Cool. So let's get started with the session on DP. Okay, cool. So before starting, like I always say that before you even start a topic, you should know that why we are even studying that topic, right? Otherwise, it's just a waste of time. So why do we even want to study dynamic programming? What are the use cases? How we should implement it, right? So I'll be going through every tiny bit and piece of it. But I assume that some of you over here might already know these things, but a slight overview or a slight, recap won't actually hurt. So with that in mind, let's get started. So what's DP or dynamic programming? Dynamic programming. So it's actually a very fancy name. Now let's just call it memorization. So dynamic programming is not nothing but just memorization. And what's that? So let's say I ask you to do a particular task, right? T1. So you do the task for me. Then I ask you to do some task T2. And let's say the only motive of doing this task was that I gave you some problem and you return me the answer for that, right? So when I gave you the task T1, you return me the answer X. When I gave you the task T2, you return me the answer Y. I gave you a task T3, you return me, let's say, A for it because its answer was A. Then I again gave you the task T1. So now would it make sense for you to again do this entire task and then return me the answer that okay, the answer is X? Definitely not. As a intelligent being, what you'll say is that oh, I'd already done this exact task before. I already know that its answer is X, right? So if I already know that its answer is X, let me directly return it to you, or let me directly tell you that the answer for this is X itself. And this is the entire thing, or the entire fancy term, what we call DP. Now, I'll be starting with the pretty cliche example, or the pretty standard example that we most of the time study, and that example is uh, about Fibonacci series. Fibonacci series. Just give me a second. Okay, just want to confirm. Yeah, cool. Okay. So what are Fibonacci series? Fibonacci series actually is f of n is equal to f of n minus 1 plus f of n minus 2, right? Where f of 0 and f of 1 are actually predefined to be 1 itself, right? So f of 2 becomes f of naught plus f of 1, that becomes 2. Then f of 3 becomes 2 plus 1, that is 3. F of 4 becomes 5, so on and so forth, right? So this is the sequence 1, 1, 2, 3, 5. And then you will be having 8. I hope you already know what a Fibonacci series is. Now, if you want to calculate the Fibonacci for any number, that is f of n, or let's say I want to calculate the Fibonacci for f of 5, right? 5 is also a big number. Let's just call it 4 to save time. So for f of 4, you'll need Fibonacci of 3 plus Fibonacci of 2. You'll add them up and you'll get Fibonacci of 4, right? So what about Fibonacci of 3? Fibonacci of 3 would be Fibonacci of 2 and Fibonacci of 1. Now, I already said that we know Fibonacci of 1 is actually 1 itself. So I know that value. Fibonacci of 2 is actually f of 1 plus f of naught, right? Of f of 0, you can say. Cool enough. So now these are actually to that particular level, or these problems are now that simple that we already know the answers to them. So the answer to f1 is 1, right? The answer to f0 is 1. 1 and 1 could get added up, right? And the answer to f2 would also become 2. So 1 plus 1 is actually 2. So answer of f2 would be 2. Now from here we'll pass on a 1. From here we'll pass on a 2, right? So the value at f3 would become 2 plus 1, that is 3. Now it will pass the value 3 to f of 4. Now f of 4 would say that I also need to calculate f of 2. So f of 2 would now again be f of 1 and f of naught, right? Whose values would be f of naught. Oh, sorry, f of naught is actually directly 1. So we can put that value over here. So yeah, okay. Yep. So directly value 1 over here, and f of naught is also 1. So 1 value over here. Then f of 2 becomes 2. It passes the value 2 to its parent. Then f of 4. So it's okay, cool. I have a value 3 plus 2, that is 5. Now, had I used this dynamic programming over here, so this step could actually have been saved, right? Because I calculated f of 2, but f of 2 was already calculated right over here. So had I used DP, so my steps would have been saved. Is that correct, or am I able to make sense over here? Is everything clear?
Yes.
Okay, cool. So had I already saved the value of f of 2, then this step would have been saved. Now you'll say that this is pretty small, this is actually a really easy thing to do. We can easily calculate f of 2. It's not a big deal and all that stuff. Yeah, you're technically right, because over here the number was actually small. So we were just talking about f of 4. Imagine we were talking of f of 1000, right? So f of 1000, you will calculate f999 and Fibonacci of 998. Now when you will be solving it, so this would be 998 and 997, right? Then you'll again solve it as f997, then 996. I hope you get the drill. Technically, this leftmost child only would actually need to be solved, because when you'll be returning from the leftmost child, you'll already be having the values to the right child, because when you'll return from this, you'll already be having the values for f996, right? You'll also be having the values for f997 and for f998, right? So technically you just had to solve for a single child, or you had to solve for only 1000 numbers in total, right? So you directly went from here to here. So it is only gonna take you like order of n complexity, because you only checked for what is f999, what f998 is. So basically f of n is equal to f of n minus 1 plus f of n minus 2, right? So in this entire equation, you just kept focusing on f of n minus 1, right? But f, when you would get the answer for f of n minus 1, that automatically would also give you a value that would be equal to the f of n minus 2, right? Okay, n minus 1, n minus 2, n minus 3, yeah. So each time you only need to solve half of the things, right? So this makes the task a lot simpler, and you will be saving a lot on time complexity. If you want to understand it, so in normal scenarios, when over here, like you can see, that this would become actually a tree. Now this actually becomes a tree, right? And the height of the tree is n. That makes sense, because this would be n, this would be n minus 1, this would be n minus 2, so on and so forth. So the height of the tree would be n. Now, what would be the number of elements at the nth level? Now, it won't be exactly 2 to power n, because it would be slightly skewed like this. If these things are not making sense to you, don't worry. These are just things I'm trying to use to explain that why DP is beneficial. But just to assume that when we would have completed that Fibonacci graph, we would have a tree like this, right? So approximately the last node would actually contain 2 to power n children in total, right? Now you're reducing that. What you're saying is you'll only do order of n computations. Initially you were doing 2 to power n computation, now you're already doing n computations. Now let's check this out in like in some terms. Like let's say your n was 10, then over here you were doing 2 to power 10, that is approximately 102 for 2 for computations. Over here you'll just be doing 10 computations. If it becomes 2 to power 20, then you'll be doing 1024 into 1024. That should be somewhere around 10 to power 6 computations, right? Okay, but over here you'll just be doing 20 computations in total. Now you look at the graph. One side you have to do a million computation, and the other side you have to just do 20 computations. So that is the benefit of using DP. Is that part is that part understandable, that why we are using DP at all?
Yes, I got it.
Okay, cool. So now what we'll do is that we'll do the same cliche example. We'll code it up and we'll try to understand that how it actually works, right? So I'll try to explain it. Firstly, I'll write the code. Okay, so this is basic code. Okay, so I'll make a Fibonacci function. I hope that everyone over here actually knows that how recursion works, right? So let me call it a recursive function, which will take a value n, and the terminating conditions would be that if n is equal to 0 or n is equal to 1. So basically n is less than 2, then return 1, right? And else, you can say else, or you can directly return it. Return recursion of n minus 1 plus recursion of n minus 2. But wait, let me do one more thing. Whenever I'm coming over here, let me print the value so that I know how the recursive loop works, right? Now let's say I want to print, or let's just call this recursive function. This is actually Fibonacci function, so let's call it fib. Okay, this also becomes fib. So does this. Okay. So let me call Fibonacci for 10, right? And let's just run it. Okay, so let me run it. Okay, so okay, it adds some input. Let me just make a new test case. Okay, so over here you are able to see that what actually happened. This code got called. It called 98765431 all the way to 0, right? Then it again started calling the elements. You can see that, right? So there's a lot of repetitions, because in a single loop, when it will be traversing its left children, it would have already seen all these elements, right? So after that, all of these computation which I was doing was actually just a wastage of time. So these many computations were actually wastage of time. I could have easily saved the values and I could have printed it. Now let's see if I increase the numbers to let's say 20, then what happens? Okay, so you can see that firstly it started going down the line, it started checking for numbers. Up till this point, it already has the values for all the numbers it actually required, right? But it didn't save it, so it kept checking again. So these are the amount of calculations it's actually doing. It's pretty massive, right? So if I can't even scroll it down, so it's pretty massive, right? Now easy way out is that I could have actually saved it. Now how do I save it? There are multiple ways of doing it, but let's say I just had a array and let me define it of 20 size, or maybe just 100 size, right? Let's put value zeros in the starting so that I know that, okay, size of array. Okay, so -1 are the dummy values. If the value is not -1, that means I have already I already checked for the value, right? So if my array of I is not equal to -1, in that case return array I, not array I but array n. Guys, it might feel a bit slow right now, like I'm not teaching at that pace, but just hold on for a moment. After this we'll try to make sets and all that stuff, so just hang around for a moment. Okay, so if we are doing this, let's see what happens. Okay, we also have to populate it, so we can say array of n is equal to this, so that the values also get stored. Array of n is equal to this. I hope that makes sense now. Let's try this. Okay, typo. I think this is fine. Okay, type over here. Okay, let's try this out. Okay, so you can see that previously there were massive number of computation, around 1 million computation or something. Now that computation have actually improved, right? So we are just doing 20 computation or something like that. So in just 20 computation we are able to calculate it, and this is exactly what DP is. Now I don't know why people make a hype about it, that it's pretty tough and it's tough to use and you need a lot of concept clarity around it. This simple thing that making an array, storing the values in it, right? Making this array and storing the values in it is actually called DP. That's it about it. Now what the other thing is that how do I know that I want to calculate this particular value only? So that there comes a concept known as states, right? So in your recursive function, when you make a recursive call, so you pass in some parameters. Now that parameters actually define what your answer would be, right? So let's say I have a function f of x, right? F of x which returns me z, let's say, right? So x is actually the state for it. So x defines what the output answer z would be. If I have a function f of x comma y which returns me z, then in that case state is defined by two variables x and y, because that actually defines what my what my answer would be. So that's the concept of states. Now the number of states you are having would actually define the size of your DP array. Over here I was just having one state, right? So only one variable was enough to define what the answer of this recursive call would be, or this function would be. That was n itself. So Fibonacci of n only depends on n. That's obvious. So only one variable was required. Now you could get into scenarios where more than one variables are required. So let's say you made some function f, right? Over there you require two functions x and y, and both of these two functions combinedly were required to return the value, right? In that case, what you can do is, while saving the states, you can use a 2D array. So a 2D array would be something like this, right? You can say it's of 100 size, it's of 100 size, and then you can save the values along. Up till this point, is everything clear? Hi guys, is it getting too boring or what?
No. I just wanted to ask one thing.
Yep.
How do I print the Fibonacci value?
Okay, so simply do a cout over here. Remove it from everywhere else. Just do it over there. That's your point, right? Okay, why did
For
it
some
fail?
reason, that is not working.
Just wait a second. I made some type of. Oh, I just declared a function over here. I'm not returning anything from that. Yeah, it would work actually. Why won't it work?
Um,
See,
I'm trying to do it in JavaScript. It's not working for me.
you probably are doing some typo. See over here, it's
Yeah,
working right.
maybe.
So even if you don't,
Yes.
like for 100, are you using DP or not?
No, I'm just trying to like
Okay, reduce the
make the
reduce the
Fibonacci
value. Yeah, reduce the value. Are you using 100? N is equal to 100 or something?
10.
10 should still work. It shouldn't. It won't work above 30 or yeah, like at 25 or 30, it'll stop working. But for 10, it should work. Probably you are messing up this terminating value. So the terminating value needs to be mentioned, right?
Terminating value should be 10, right?
No, 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 no.
Whoa, I mean 1, right? So for 10, it should be 89.
Less than or equal to 2, because 1 and 0 can both be the terminating values. Let's say you're calling fib for 2, right? So when you'll call fib of 2, it will ask for fib of n
Okay,
minus
actually, I
1.
got it.
You were
It
calling,
worked. It
right?
worked.
Yeah.
Yeah, what happened was in the statement, if n is smaller than 2, I was returning 0 instead of 1.
Still
And
that
that was
shouldn't. Okay,
that.
okay,
No, I was returning 0 now, so it
okay, okay, okay,
wasn't adding up 1.
got it, got it.
Yeah.
Makes sense. Fine enough.
Yes, thanks.
Acha, so cool. So one thing I wanted to emphasize is that a lot of people over here who are already doing CP and stuff still sometimes get stuck on states, right? So I wanted to explicitly discuss about states because this is something I feel a lot of people get stuck on. Now, how can we reduce the states? So if I have two variables x and y which are determining the value of z, then there's no way I can reduce it, right? I'll have to save both x and y. Sometimes what you can do is that you start understanding that okay, x is also dependent on y. Now let's say my x value is always 2 into y plus maybe some integer, right? 249, like this is something I just manually made up. So let's say this was a function that was always working, right? If I'm able to determine such kind of a function, then over here I don't need a 2D array. So I'll say that okay, I can work with a 1D array itself, right? 1D array of x itself. And how would I utilize y whenever I will require it? So even in the parameter of it, I don't need to pass the y, because whenever I need the value of y, I can simply say okay, or whenever I need the value of x and I want to calculate it from y, so I can easily say that it's 2 into y plus whatever gibberish it was. Does that make sense?
Yes.
Okay, guys, anyone else? Because I think Abhay is in first year, right? But you guys are actually already doing CP. So is this kind of a thing relevant, or have you sometimes like?
Yeah, the DP basic understanding is clear. Just think this some question. I know how to apply the DP
Mm-hmm.
on the questions, but don't know the where to start like the DP. This
Okay.
question is DP related or any graph related, just like that.
Okay.
Deep, basically DP on graph questions.
Got it. So see, the thing is that when you are trying to apply DP, now a lot of people. So okay, I wanted to discuss this particular thing at the last, but never mind. Okay, so DP are also of two types. Let me just erase it entirely. So when we're talking of DP, there are actually of two types. One is the bottom up DP, and the other is the top down DP. This actually uses recursion, right? And this uses weird logic, I'll say, like okay, just logic. So what I'll suggest is that as a beginner, so you're not someone who's already masters or grandmaster on code forces. So as beginners, always try to go with top down DP. So top down DP example is just what we did right now, that we'll make a recursive function and the recursive function is gonna give us something, right? And then we are gonna memorize the states. So always start with top down DP, or even don't think about top-down DP, just simply think about it as a recursion problem, right? So as and when you think about it as a recursion problem, you'll be able to develop the solution for that. If you're not able to do it even with a recursion problem, then you need to study more, because if you're not able to do it with the recursion, then that means your logics are not building for that problem, right? So it's not even about DP, but the simple fact is that you're not able to make the logic for that problem. Okay, so as soon as you are able to make the recursion problem, then start memoizing it. Right. Then the other thing is that you need to see that when you're memoizing it, what are the time constraint and the space constraint. By that I mean, is your 2D array, if I'm using a 2D array or whatever you are using, is it being inside the well-defined limit of time constraint and space constraints? It could be the case that it's going like, it's taking a memory of 10 to power 9, 10 to power 9 or 10 to power 10. Now that is several GBs. So 10 to power 10 is actually 10 GBs if it's 1 byte is each individual element. This is definitely gonna give you a MLE or a TLE even. You don't want anything of the order of 10 to power 9 basically. 10 to power 8 is itself risky. 10 to power 6 to 10 to power 7 is the playing range we target, right? So you don't want anything of this category. Now let's say your states, there are two states that were A and B. By states I just mean that this was a function, right? Over here you are using two variables, int A and int B, right? And then you were saying that, okay, so the answer is, okay, let's just call it DP now. So DP of A and B, right? And let's say your A was going from 0 to 1 E5 and your B was also going from 0 to 1 E5, right? Now technically when this kind of a case would happen, so your DP array would take 10 to the power 10 space in total, right? It would get multiplied, so in total it's gonna take 10 to the power 10 space, and this is gonna give you a TLE or a MLE. Now how do you get rid of that? Then we have to start thinking about that how can we reduce the number of states, or how we can incorporate the number of states. Now what do I mean by incorporation of number of states? I'll give you a very good example for that. So let's say we are working on array on maybe some matrices, right? And matrices have two values, let's say I and j, and these can be independent, right? Because my I doesn't depend on my j and stuff. But let's say I have been given a constraint that my I plus j is equal to some letter m. So this is some constraint that the question additionally laid upon. So now with that what I can say is that I'll only be storing my I, right? I'll only be storing my I, and whenever I'll need my j, I'll just subtract it from that. Or is there another way of doing it? Yes, there's another way of doing it. Instead of using a 2D DP like this, what other way thing I can do is that, let's say the range of A was 100, right? Yeah, let's say it was 1000, and the range of B was also 1000. Now instead of using a 2D DP, what I can do is I can make another number C, where C would be A into 1000 or maybe 10,000 or something like that, whatever you want it to be, plus B, right? And whenever you want to extract values from C, whenever you want to get the values of A and B from C, you can simply say that B is equal to C modulus whatever this value was, and B is equal and A is equal to C divided by whatever this value is. This makes sense? Guys, I lost you, or does this make sense to you?
Yeah. Makes sense.
Makes sense to you? What about others?
Can you explain that once again?
Which one?
Just that part, ABC part.
Okay, so A and B are two numbers, right?
Hmm.
Now A and if you want to store them two numbers, then you need a 2D array like this. Make sense?
Yeah.
Okay.
Yeah.
What I'm saying is, rather than storing this number separately, let's combine these two numbers. But when you combine these two numbers, it should be in a way that you're able to extract the information as well whenever you need it, right? So let's say my A has currently a value 80, right? And B has some value 123, right? So let me define a combination formula. So my combination formula is that I'll multiply A by 1000.
Oh, now I got it.
Cool.
Okay. And you used 10 to the power 5 earlier because that is the maximum range A and B can get to, right?
Right.
Okay.
Make sense?
Yeah.
Cool. So these are the ways, or these are the tricks that you can commonly use to reduce the time complexity or space complexity of your DP approach, so that it doesn't give the TLE. Other than that, DP is actually nothing. It's pretty a hyped up formula, right? But as you grow, so you should start learning about bottom up DP as well, because this is something that is not that intuitive. It's more about practice. So if I ask you that, okay, get me the answer for a 0-1 knapsack, right? So I hope everyone knows what a 0-1 knapsack is. So you'll be able to give me that using a recursive call. It's pretty intuitive. So how does that work? So let me firstly tell you that how do we select elements from, like how do we come up with combination of elements, or how do we come up with sets? So let me go to my iPad. So let's say I want you that I'm giving you an array, right? That is 1, 2, 4, 6, and maybe 5. Cool. From this array, you have to select 3 elements, right? Such that their sum is maybe like, okay, not just 3 elements. It can be actually 3 elements as well. Yeah, just let's do that. So 3 elements whose sum is 9, right? How would you do that? Or let's just say change the sum a bit more. So their sum actually needs to be 8. Fine. So one way of doing it is the brute force way. So every element, you will say that every element can either be selected or neglected. So I'll start with 1. I'll say okay, so this is the DP approach. I'll say this is the array I'm having, 1, 2, 4, 6, 5. You'll say in one case I can accept the element. So if I accept the element, so the answer I'll be having, or the sum currently I'll be having, is 1, and the remaining elements would be 2, 4, 6, and 3. In the other case, I'll not be accepting the element, so I'll not be accepting it, so the sum would still be 0. The elements now I'll be left with would be 2, 4, 6, and 3, right? So over here, now you'll again say if I accept the element, the sum would be 3, right? If I reject it, the sum would be 1 itself, and over here you'll be having 4, 6, 3. Here also you'll be having 4, 6, 3. If you accept it, sum is 7. If you reject it, sum is 3. 4, 6, 3 over here as well. Oh, sorry, 6 and 3 are remaining over here. Now you'll say that, okay, so cool. So over here, if you accept this, then your sum becomes 9. If you reject it, your sum remains 3. Remaining element is 3. You get the drill, right? So in this way, we try for all the sets. So for every element, there would be 2 possibilities: either to accept it or either to select it. Now this is actually a pretty boilerplate code. So I'll just request every one of you to go through this, because this actually comes really handy when you are coding. So what you have to do is that let's call it DFS. Now, even if you don't know about graphs and stuff, it's completely fine. Just remember I call it DFS. You can actually call it recursion. Now you can say index, or just provide it with a vector. So vector, okay, vector int v and the current index. Then you'll say that if your index is already outside the range of the array, that would be given by v dot size. Then in that case, you have to simply return, or you can return 0. Okay, there had to be a current sum as well, int sum, right? So in this case, you can return sum. Else you'll have 2 possibilities. Now what are the possibilities you have? You can either accept it. So if you want to accept it, then it would be v idx plus 1, and then your sum would actually get incremented by the particular value that would be at that particular index. Or in other case, you can see that I'm going to neglect it. So if you're going to neglect it, then the sum is going to be idx plus 1 comma sum. Okay, if here I've used idx, so idx it is. Okay, this makes sense. Now what about the terminating condition? In the terminating condition, I can do whatever I want. So over here, I can say that, okay, I already have the sum, so I'm gonna check something. So let's say there was another variable, int required, that was placed over here. If the sum is equal to required, then I can say that, okay, found it. So cout found, right? Let's just test it because we have already made it. So let's just test it a bit. Okay. In the solve, I'm gonna say, okay, int n, then I'm gonna take the value, then I'm gonna take a vector, take the, okay, vector v, I'm gonna take the input for v, right? I'm gonna set the required to some value, maybe 10, right? And then I'm gonna call this recursive call v idx. Idx is actually 0. We'll start from 0 itself. The current sum is also 0. Let's test it if it works. So let me remove this. So let's say that we have 5 indices, right, or 5 elements in total. The elements are 1, 2, 3, 4 and 5. Do the sum up to 10? Yep, actually they do. So let's test it. It's running now. Let's see what happens. Okay, I messed something up. Let's see. Okay, this has to be void. It's not returning anything, so maybe 6f. Now I'm getting a 6f over here. Okay, idx. Okay, I forgot to return. Found. So yeah, it's working. So basically it's going at every element. Then it's selecting two choices. One of the choices that will not consider the particular element, the other choices I'll consider that particular element, and it will go forward with it. Now this is the way recursion actually works, and this is the standard boilerplate code that you're gonna use whenever you are gonna try that. I have two options: either I can keep it in my set or I can neglect it from my set. Now how can we use
One question.
Sure.
It said found 3 times. That means it found 3 combinations,
Yep.
right? Okay.
Okay, let's just verify it. So one was 2, 3 and 5. That's fine. One was 1, 4 and 5. That's also fine. Which was the other one? Okay, 1, 4, 5, 2, 3, 5. Which was the other one?
I think 3, 4 and 1. No.
Nope. Okay, let's good question actually. Let's there's one way to do that if you want that too. So let's
Will be 1, 2, 3, 4.
Oh
1,
yeah.
2, yeah, right. Cool. Thanks, Abhi. Okay. So you got the point at how to do this, right? Now,
Yep.
can we? So over here you said that it found it 3 times, right? So that was a waste of time because we had already found it and still we tried doing that. So there are two ways of neglecting it. Either you could have said that int found, right? Or sorry, bool found. You could have set it to 0. Found. And found was initially set to 0 or false, right? And as soon as this happened, you could set found to true. And over here you can say that if you have already found something, then return. Okay, then return basically means don't do any of this processing. I already got an answer. Let's test it. Cool. So now it only prints it one time. Now there's nothing related to DP over here, right? Now DP can actually be applied. I can say that instead of return like trying till the end, what you do is that you actually return the values if in case you have already found the answer. That is something we can do. The only reason of explaining this kind of a code to you was that this comes in handy while doing recursions. And the first step to learn DP is that you actually are comfortable with recursions per se. Now, if you don't know how to make sets with it, right, you'll never be able to do DP on let's say for DFS or on other problems which actually require you to consider the possibility of adding or removing particular elements. So if this thing becomes clear to you, you'll be able to solve a lot of questions on maybe lead code. I'll not say that you'll be able to solve a lot of questions on Codeforces because of this, because that's gonna come in the advanced topics. But the entire motivation of this lecture was to explain you how things work in recursion. I hope that fundamental clarity is now present over here. I'll be turning back over here.
Yes.
So anyone else like, do you have any doubts over here? Uchiha, why am I not able to hear you? No voice seems. Is she still here or is he still here?
Nope. He left.
Okay. Anyway, cool. So that's about it. I don't want to extend this lecture a lot. We already have a GFG contest up and running. So with that, is everything clear? Is the basics of DP clear? Is there anything else you want me to explain? Cool guys, then thanks a lot for watching this video or like being in this session.
Thanks a lot, sir.
Cool man. Bye bye.
Bye bye.